All right, let's begin. Um, so, for all of you who were whining and complaining and griping about how hard it was to take the second COVID vaccine, um, and asking for extensions and that kind of thing, and I was like, oh yeah, right, uh, you know, you're talking nonsense. On the other hand, I just took my second vaccine yesterday, and I was all fine until last night at like 4 a.m., where I developed the chills. Um, so clearly, uh, you know, um, maybe I'll be. I mean, I was giving extensions anyway, but I'll be a bit more understanding. Because I don't know. I mean, I'm definitely you know I'm just telling you my physical condition just in case I end class early or do something stupid like that. But the point is, yeah, I got Pfizer. Uh, was for me. I live down in PG County, so I went to that Six Flags fairground place, and it was definitely. I mean, I'm not. Let's admit here, I'm not really complaining for myself. I'm just saying that, like, I the way that my brain works is like when I get an extension request, I'm usually just like, okay, they're making stuff up, uh, you know, but my practice is generally. So let me explain what my practice is. Students tell me all kinds of weird things. Never know what is true or not. And this is my practice. I don't really care. If you need an extra day, that's what you get. So, yeah. So I mean, so anyway, I thought like, oh yeah, I'll be fine. It's not a problem. So anyway, that's just why I'm kind of out of it today. But really, we shouldn't be talking about this at all. We should be talking about the far more interesting um, than the fact that I've got some minor symptoms. Is BigO. So yeah. Um, I had a professor here, actually. I visited his office. I know that this is completely irrelevant. He was a brilliant guy. Um, he was in the math department, and I visited his office, and he was kind of acting weird. And I realized, and he told me that he was on some pretty heavy painkillers, and I'd asked, I asked, what the heck is going on? And he told me, he was like, oh yeah, yesterday when I was teaching my class, I started feeling some pains, and this was, 15 years ago, so nothing COVID related or anything. Anyway, he started feeling some pains, but he went through and taught his class, and then he went home, and I think it was his wife who made him go to the hospital, and as soon as he got there, they were like, your appendix is about 10 seconds away from bursting. So they took him into surgery. So, apparently he just pushed through. So, comparatively, I'm definitely a weakling. Um, so, yeah. Anyway, so don't let your appendix burst. Teaching a class on matrix analysis is not necessarily the most high priority in your life. Yeah, I mean, he was fine. He showed up the next, it was a few days later, I think, after his surgery, and he was telling me, he was still on some painkillers in his office. And I don't know if you've ever talked to people on painkillers. Sometimes they have short-term memory loss, so I basically ended up having the same conversation with him like twice. Because he had forgotten the beginning of the conversation by the time we got to the end. I think the moral of the story is, take some time, right? You don't need to come back a few days after you get your appendix out. So, anyway, so that's a completely irrelevant story. It just reminded me of my complaining. So yeah, let's start to discuss BigO. Well, right now, here's the problem with giving general extensions, is that if I start doing that, we're going to push past the end of the semester. So I'd be okay giving extensions on certain things, but, Okay, let's talk about BigO. I said something about extensions for those who suffered from vaccines. Yeah, if you email me, I generally have been giving individual people, an extra day or two if they beg me to just write. So, okay. Where am I going with all this? Yeah, BigO. So, what's the point of algorithmic analysis? And so the answer is that some algorithms run at different speeds based on the input size. Okay, so it's as simple as that. Algorithms run at different speeds based on the input size, and so as you know, for instance, the number of steps it takes to do a binary search is approximately log n, right? And you might say, well, should be lg of n, something like that, right? And we know that the number of steps in a linear search is approximately equal to n. And really what I actually mean by this is some constant times this, and maybe some other constant times this, but whatever. Yes. So basically, let's go over the mathematical definition of BigO. So what is the definition of BigO? The definition of it is this. Actually, let's use some LaTeX. LaTeX is good. So let's see here. F of n is BigO of g of n when, and let me say, there is a constant c and a constant, or n, so that, whoops, I want this all to be in the inbox, so that when, let's see, little n is bigger or equal to n, then f of n is less than or equal to c dot g of n. So let's have that all written out, and hopefully it'll render properly, because it's a very long expression. Let's see how it goes. So, okay. So the point is that here's the technical definition of BigO, right? There's a constant c and a constant n, such that when little n is bigger than or equal to big N, f of n is less than or equal to c, and that should be that dot should be multiplication. It should not be it should not look like a derivative or something like that. If you know physics derivatives, like, you might think that that's a derivative, but it is just a multiplication dot. Let's see if this one rendered any better. No, it didn't. Okay. Okay, cool. So this is the definition of BigO, more or less. But, what does it mean? And so the first question is, what is this in symbol that I used here? And so basically, I use this symbol, and the reason why I use it is because I find that a lot of computer science books tend to abuse notation pretty hard. Sometimes instead of using a symbol like this, they'll actually use a symbol like f of n is equal to big O of g of n, which you'll see why I don't like that in just a bit. Anyway, so the point is that basically this is the operative thing here. This is the thing that makes everything work. So we want f of n to be less than or equal to c times g of n, okay? So let's go over a few examples of things that are actually big O of other things. So for instance, right, n squared is big O of n cubed. And let's argue why that's the case. So you might ask, well, why is this the case, right? Why is n squared big O of n cubed? And the answer is, well, can we find a constant c such that n squared is less than or equal to c times n cubed? And the answer is yes, we can. So because remember, in general, we're looking for a constant c that'll do this, okay? And as it turns out, in this case, we can actually just pick c is equal to 1. And here's why we can pick c equals 1, right? The argument is that n squared is always just less than or equal to n cubed. And that's not all. I mean, I shouldn't say that's always true, because when n goes negative, it's going to be a problem. When n is between 0 and 1, that's a problem. But I'm also going to set our constant, say, little n, or big N, is also going to be equal to 1. And so the reason why we don't care, so basically there's a moral of the story. We don't care about negative n's. And the reason why we don't is because n represents an input size, okay? And so generally, negative input size doesn't really make sense. So when we talk about functions, we're only really talking about when n is bigger than or equal to 0. Right? We don't really care what happens when n is equal to 0. We don't really care what happens when n is equal to negative 5. Right? So we don't care about that. We only care about what happens when n is sufficiently positive. Right? So that's one thing that big O requires. Okay. And so then, what's up with this constant c? Right? Yeah, basically, yeah. What's up with this constant c? Right? And so let's look at some other examples. So let's ask the question, is, say, 5n squared plus 2n plus 1, is that in big O of n squared? And let's type this out and then render it, and then we'll discuss why it is, right? So the question is this true, right? Is it true that 5n squared plus 2n plus 1 is in, and that's how I'm going to talk about this epsilon symbol. I'm just going to call it in. Is this in the class of O of n squared? And the answer is yes, right? And the question is why? And so the answer is actually what we can do is we can pull a little trick. We can say the trick is that you basically say, well, okay, I have this constant c, right? So what if I, instead of looking at it like 5n squared plus 2n plus 1, I just said, okay, I want to set c is equal to 5 plus 2 plus 1, right? And so that's going to be equal to 8. And so then the question becomes, right, is 5n squared plus 2n plus 1 less than or equal to 8 times n squared? And the answer is, yes, it is, right? And why is this the case, right? Because 5n squared is equal to 5n squared, so we have the 5n squareds on both sides. And then I basically just rely on, there's an argument that I rely on here. Basically, I'm just going to rely on the fact that n to the, a is less than or equal to n to the b, right? When a is less than b, and say n is bigger than or equal to 1. So this is the argument I'm going to rely on. Okay? And I think most of you should know this from calculus, right? Basically, if you have two polynomial things, right? Or I don't even care if they're integer powers, right? It doesn't really matter what they are. As long as a is less than b, then n to the a is less than or equal to n to the b for when a is less than b and n is bigger than or equal to 1. So, I mean, you could prove this over and over, but I'm just going to assume that this is just kind of a fact that we know, okay? And you might ask, well, why is this the case, right? And the answer is, well, I guess what you could do I actually majored in both math and computer science when I went to college. So, point is that if you divide, right? So let's divide both sides by n to the a. Then what you're going to end up with is here. What you're going to do is you're going to end up with n to the b divided by n to the a, and that's just equal to n to the b minus a, right? And on the other side, you have a 1. And so the question is just like, is n to a positive power, right? So this is an equivalent statement here, right? Is it true that n to the b divided by n to the a is n to the b minus a? Yes, because of exponent rules. And is it true that 1 is less than or equal to n to the b minus a, where b minus a is positive? Yes, it is, because, I mean, you can just look at the graphs. I don't really care how you prove it. You can look at the graphs, whatever, right? It's always going to be bigger than 1, right? At least when n is bigger than 1 and all that stuff. So the point here is that polynomials, or, things with exponents, are always increasing like that. Okay. So now here's another question. Is, let's say, n squared in big O of 2 to the n? Let's ask that question, right? And so you see why this is a different question than the polynomial question, right? The polynomial question was, oh, stupid thing, didn't render the parenthesis. Okay, let's see if it will do better this time. There it goes. The LaTeX feature is not perfect. It doesn't always render the exact thing that I type. But anyway, okay, so save as. Let's see here. Okay. All right, so is this true, right? And the question is n squared less than 2 to the n? And the answer is, it is and it isn't. It depends on exactly where you're looking. But, for the negative values, you could always say something like, for negative values, n squared is bigger, right, than 2 to the n. True. But remember, we don't care about that. And then there's also the fact that maybe between, say, 0 and 1, well, actually, I think even between 0 and 1, 2 to the n is going to be bigger. I mean, so there's a bunch of different ways to look at this. The one way to look at this is actually just to look at the graphs of the two functions. And so if we look at the graphs of the two functions, we're going to quickly see, so here we're going to quickly see what's up with n squared and 2 to the n. So if you notice here, n squared is in red, 2 to the n is in blue, and you might say, well, hey, look at this. Between, where is it? Between n is equal to 2 and n is equal to, I guess, about 4, as it turns out, n squared is actually just a little bit bigger. Like, look at that graph. N squared is a little bit bigger than 2 to the n. But remember what BigO gives us. BigO says we don't care about these early values, right? What we actually care about is really, I mean, in a sense, and I think I'll just say it up front, is we care more about like the limit as we go to infinity, right? So let's think about that as the limit as we go to infinity, and you see that the blue line is 2 to the n, this is n squared, and so, yeah, exactly. So the thing is that what you're going to actually really be doing is, in this case, you can even just look at, for instance, the limit, right? Say the limit as n goes to infinity of, and let's look at the fraction of n squared divided by 2 to the n, right? And so let's look at that and see what we're about to get. So here we are. Here's this limit that we're going to look at, right? And you might say, okay, I'm a fan of L'Hopital's rule, like a lot of people. So let's apply L'Hopital's rule here, right? So this thing is equal to, for instance, say, you know, you take the derivative of the top, 2n, the derivative of the bottom, which is, as it turns out, it's the natural log of 2 times 2 to the n, right? So that's the first step. And then you'll do it again. Let's see, here we are. So this is the first step. And then let's do it again, right? We always have to, apply it until we're... And then the second time, when we take the derivative of 2n, we'll get 2. And then here, unfortunately, when we take the derivative of 2 to the n again, we're going to get the natural log of 2 squared. And so that's going to be it. So if you think to yourself now, like what happens as, what happens here, right? So here we have n squared goes to 2n, goes to 2. Here we have 2 to the n goes to natural log of 2 times 2 to the n, goes to natural log of 2 squared times 2 to the n. But remember that this is just really a constant here, so it's not going to affect our result. This is, in the end, 2 is just a constant. So now we have the limit of 1 over 2 to the n as n goes to infinity, right? And n goes to infinity, right? So 2 to the n is going to go to infinity way faster. So basically we have a 2 over infinity, or we have a 2 over natural log of 2 squared times infinity, and the answer to that is going to be 0. Yep. And so this is an even more powerful result. What basically we're saying is that eventually, right, when you take this kind of limit, what you're actually saying is that eventually, not just that f of n is going to be less than or equal to c times g of n, right? That's not what you're saying. What you're actually saying with this kind of limit is that f of n is less than or equal to basically g of n in such a way, it's hard to even describe. So I guess what I really mean is that f of n is less than or equal to c times g of n for any n, right? Because what's about to happen is that it doesn't matter what constant you put in front of g of n, and what this is called when one function will dominate another function. So f is dominated by g, which just means that f divided by g, the limit of f divided by g, is equal to 0. So well, the theory at least, right? I mean, well, yeah. Okay. So basically this is the point here, right? The point is that this is an even stronger result than it being big O. So this is actually saying that f is so much less than g that f divided by g will eventually go to 0 as you go to infinity. All right, so let's ask some other questions, right? So let's take, for instance, I don't know. I guess here's a question, like, is 5n squared big O of n, right? And so let's do a false one. So here's a false one. And so let's describe how we can understand that that one of these kind of questions is false, right? So here's a false one, right? We've only seen true ones so far, so this is a false one. And so why is this one a false one? Now you can always say, like, okay, I'm going to use the old result, right? The old result says that, you know, n squared is going to be bigger or equal to n, you know, eventually. And that's true. So basically what we have here is that it doesn't really matter what constant you pick, right? if you have something like 5n squared, right, and you're going to say, let's claim, so this is, I guess this is a good example of a proof by contradiction. So what you're going to assume that it is big O. And so then what you're going to do is, you're going to say, okay, therefore, there is some constant, C and N, or I guess there are some constants C and N, so that 5n squared is less than or equal to C times N, right? That's the result that's required. Okay. But then, if we divide out by an n, what we're going to see is that the claim here, so then what you're going to do is divide this by n. And then what you'll see here is that 5n, right, has to be less than or equal to a constant c. Yeah, I don't really necessarily want the comment section to devolve into a vaccine debate. I mean, unfortunately, regardless of what your opinion is, you got to take it for next semester anyway, because they're going to mandate it. So that's why you're going to do it. It's because you've been told to do it, and that's it. But the point is here, right? Well, so here's the thing, right? So is it true that 5n is less than or equal to c? And the answer is, well, no, because whatever c is, what you can do is you can say n has to be less than or equal to c divided by 5, right? For all n, yeah, you can pick, right? And so the point here is that it doesn't, what you do is then you say, oh, well, I know I can just pick n is equal to, say, 2 times, or even n is equal to c, right? And so the one you're going to be saying is that c is going to be less than or equal to c divided by 5, and that's just false, right? Okay. So this is an example of a proof by contradiction. And I know that we haven't done any real computer science here. This is totally a math section, but I'm just doing it because I feel like we'll do the math, and then I'll describe how you apply it to computer science in a few minutes. So, okay. So here's the thing, right? This is what a proof by contradiction does. The structure of a proof by contradiction assumes that something is true, right? But this thing is probably false. So we assume it's true, and then we write down the definition of what it means to be true, right? What it means to be true is that 5n squared has to be less than or equal to c times n for some kind of, some kind of c. I don't know what c is, but whatever it is. And then, right, what we're going to do is we're going to divide by n, so that, here we go. And then at this point, you should be thinking to yourself, well, it's pretty impossible that 5n is going to be less than or equal to c for all n, right? Because, again, if you just literally pick any c, or I'm sorry, you pick any n that's bigger than c divided by 5, then it's going to be false. So the point is that this has to be true for any n you put in here, but the point is that it just can't be, right? So, since it can't be true, and we see, oh, there's a false statement here. So, what happens, right? What happens if you see a false thing, right? And so the answer is, right, there's a whole bunch of possibilities. There's a lot of logical possibilities. One, all of math is contradictory and doesn't work, right? That's possibility number one. 2, and this is the one that we generally go with, right? So it's possible, that it's logically, theoretically, philosophically possible that we've just disproven that math exists, right? Or here's the second option, which is probably a little bit more conservative, right? Meaning it's not quite as aggressive of an assumption or aggressive of a conclusion. Our conservative option is this. We don't assume that we've broken all of mathematics. We just assume that the one assumption that we made, right? We made a single assumption, which was that, and that single assumption was that 5n squared is actually big O of n. So maybe that's false, right? right? So this is the one we generally go with in mathematics, right? This is the one. Yeah. I mean, technically, you know, you could always assume that we've broken something else about mathematics, but in general, the first thing you do is you look at the assumption. You look at the assumption that you've made, and you say that assumption was probably wrong. So then what you say is, therefore, 5n squared is probably not. Well, in this case, is definitely not big O of n. Okay, so let's do a true one again. And then, we'll do this for a little bit longer, and then we'll do a little bit in terms of... so I want to argue that log n is big O of n, okay? So I want this fact. I want to prove this fact. So this one is actually a true fact. Okay? And the reason why... So here's the question. So the first thing we're going to do is we're going to look at the graphs. Okay? Let's look at the graphs. So let's take this. Let's just call this n. And then we'll call this log n, like this. Right? And it doesn't matter. You might say, well, what if you do, instead of that, you do natural log, right? Fine. Don't care. So pretty easily, just from the graphs, you see that it's definitely, right, n is going to be way larger than log n, right? But how do we prove it algebraically, right? So from the graphs, you see that it's obviously true. And I promise you, as you zoom out, there's nothing where log is suddenly going to experience some big jump, right, and shoot up higher than n, right? As you zoom out, what you see is actually that log n looks like it's going to kind of smush itself into 0. Even though it's not actually 0, the thing is that relatively, compared to n, it looks like it's getting smashed. And so as it turns out, this is exactly what we mean by dominance, right? And so if we did something like y is equal to the natural log of n divided by n, and we kind of zoom in here, what you're going to see here is that the natural log of n divided by n ends up looking like it's heading in towards 0, right? So that's what this thing ends up looking like, and that's exactly what it does. So, I mean, the one important thing to realize about... So there's a few important things to realize about log. The one important thing to realize about log is all logs are basically the same, and especially when it comes to big O. And here's why. And you might say, but logs are all different. Come on, you're being crazy here, and I hear you. But logs, what do I mean by logs are all the same? I mean that if you have the log base a of x, right, that's equal to the log base b of x divided by the log base b of a, right? And so I don't know if you remember your log base change formula, but here it is. So, where is it? Here it is. Here's our log base change formula. And then, you might think, well, that's really complicated. I don't completely understand everything about what's going on in this log base change formula. But here's the important thing to realize. This, right? This thing here, the log base b of a, so x is our variable, or n is our variable, right? So if x is equal to n, or n is equal to x, or whatever, that's our variable. A and b are just numbers, right? So what do you know about this log base b of a? I don't really know exactly what it is. It might be complicated. It might be really, some transcendental number. It might be, but it's a constant, right? So logs, it doesn't matter what log you're talking about, whether it's log base 2, natural log, meaning log base e, log base 10, log base 17, whatever. They only differ from each other in terms of a constant. And then you remember, big O gives us this constant c for free, right? So basically, this log base change, this log base b of a, can always just get sucked into the constant c. So that's why when I say logs are all basically the same when it comes to big O, Yeah, log base pi, sure, that's not a problem. There's no problem. So, I mean, I don't necessarily think it's the most useful base, but it's definitely a base. So this thing is just saying the log base a, so you can put a natural log in here, you can put log base 10 in here, you can say log base 2, log base e, all kinds of things, right? Log base pi, it doesn't matter, because they only differ by a constant. So that's the moral of the story in terms of logs. Logs are basically all the same up to a constant. Literally, they are just scale factors of each other, which is kind of a cool fact. So basically, all logs are just a scale factor of each other, right? Cool, right? That's a really cool fact, okay? So anyway, okay, so let's get back to proving our favorite statement that log of n is in O of n. And so you see, right, from the graph, we see that it dominates. From the graph, we see it probably dominates, right? But how do we prove it algebraically? And so the answer to that is, I don't know, let's take the limit, right? Let's be lazy and take the limit of, as n goes to infinity. And you see that I'm being extraordinarily kind of willy-nilly about whether or not the n is a discrete variable or it's a continuous variable. I'm sure that the true mathematician might argue, well, you can't take the limit with n, you have to take the limit with like a continuous variable like x, because otherwise blah blah blah, like you can't really take the derivative, and I really do not care. Wow, look at how badly that rendered. Let's delete that, it never existed. Okay, let's try it a third time, because that really, let's do it again. One last time. Let's do this one last time and see. Here we are, that's perfect. Natural log of n over n. So, okay, so how do we prove this algebraically? We're actually going to prove the domination, and we're going to use L'Hopital's rule as usual. So what we're going to do is we're going to say that this is equal to, what's the derivative of natural log of n? And the answer to that is, it's 1 over n, right? And what's the derivative of n? The derivative of n is equal to 1, right? So let's see here. Hopefully this renders nicely. Oh, look at that. It did. So what is the limit as n goes to infinity of 1 over n, right? The answer to that is, basically the point is that it's 1 over infinity, which is equal to 0, right? Maybe I'll actually just render that out. And I mean, I'm being very, I guess technically, I'm actually a fan of using the extended reals to some degree, meaning that I actually think I'm completely okay with infinity being a number. It's a special kind of number, but it's a number, right? And 1 over infinity is just 0, right? That's all you have to say. That's right. So what do we know, right? What we know is that if the limit is actually 0, then what we can say here is that this thing, natural log of n, is less than or equal to any constant, right? Natural log of n is less than or equal to any constant times n, right? Eventually. And I don't care whether NEC is 1 over a million or 1 over, who knows, 1 over 10 to the 10, right? Eventually, natural log will be less than that. Okay. Okay. So here's the last thing that I want to say in terms of all the math. I know we've gone through a lot of math here. The last thing I really want to say in terms of all the math is that generally you have a hierarchy. Let me remember, is it of functions? And so let me explain what I mean by that. We know that, for instance, constants are always less than or equal to, say, log functions, right? Which are always less than, say, polynomials. And really, I mean, when I say polynomials, what I mean is like n is less than or equal to n squared is less than or equal to n cubed, dot, 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 right? And then eventually, I don't care what power you have, it's always less than, say, 2 to the n, right? Where 2 to the n is just a stand-in for exponential functions. And then finally, what you'll end up with is, so constants are less than logs are less than n squared, less than n cubed, blah, blah, blah. And finally, less than exponential functions, which are then less than factorials, right? And the reason why, so for instance, the reason why factorials are bigger, right? So let's look at 2 to the n and try to prove that it's less than or equal to n factorial, okay? So remember what n factorial is. Did it render? No, it didn't. Let's try again. Man, it's fighting me. It doesn't want to render. So, okay, who cares? Let's just do it this way. Why is 2 to the n less than or equal to n factorial? And here's the reason, right? 2 to the n is equal to 2 times 2 times 2 times 2 times 2 times 2, right? And this is n times, right? Okay, cool. Now, what is n factorial equal to? N factorial is equal to n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1, right? And there's n total terms here as well, right? So there's n terms in both of these. And so what you can do is you can actually just compare, right? And you might say, well, for n is equal to, say, 2, it might not be the case and blah, blah, blah. But remember, BigO doesn't care about small n's. So here's the reason. The reason is because if you look at them individually, right? Now, this one is a little bit different, right? 2 is bigger than 1, so that's a problem. But the next one is 2 is equal to 2, so that's okay. The next one is going to be 2 is less than 3, right? So they're equal here. Now they're less, right? 2 is less than 4, 2 is less than 5, 2 is less than 6, right? So basically what we're going to see here is that 2 is equal to 2, 2 is less than 3, 2 is less than 4, 2 is less than 5, 2 is less than 6, all the way down to 2 is less than n, right? And so what we're going to do now is just multiply down both sides, right? And so what we're going to do, and once we multiply both sides, you're going to end up with n factorial on one side, and you'll end up with, in this case, 2 to the n minus 1, right? You'll end up with, unfortunately, 2 to the n minus 1 because we haven't done this completely, and n factorial. But how do we make this into 2 to the n? The reason why it's not 2 to the n, it's 2 to the n minus 1 is because the n is equal to 0 term. This one here is missing. But we can kind of, here's the trick. We can actually do something like this. We can say 2 times 2 is less than or equal to 4, right? Is equal to 4. And so now we get an extra factor of 2. Because the problem is that if we just looked at it like this and we said 2 is bigger than 1, this would be a problem, right? So we can't do this. So here what we're actually going to do is we're just going to take this 2 and stick it in with the 4, or I'm stick it in with another 2 and say whenever n is bigger than or equal to 4, we're pretty good, right? Because here we'll just have an extra 2. And that's all you really got to do. So that proves, right, that's like it's a non-calculus proof. It's just I think, in a way, it's always good to do like both calculus proofs and non-calculus proofs. Because sometimes the non-calculus proofs, like a proof like this, really makes you understand exactly what's going on, right? Because here you're saying 2 is equal to 2, 2 is less than 3, 4 is equal to 4, but then 2 is less than 5, 2 is less than 6, 2 is less than 7, all the way down to 2 is less than n. And when you multiply a whole bunch of stuff that's less than or equal, you're going to get less than or equal, right? Technically, you're going to get strictly less than. So that's what we got here, okay? All right. So, and there's another fact. So here's the other reason that you might be able to argue that exponentials are less than factorials, and the reason why is because of Stirling's approximation, which you'll probably see later on in your computer science career, but whatever. So let's talk about Stirling. Stirling's approximation. And so basically what we're going to say is that n factorial is approximately, I think it's, what is it, 1 over the square root of 2 pi times n times n to the n divided by e to the n. So this is a, ooh, I committed a latex sin. So is n considered a polynomial? N is definitely a polynomial, right? I mean, it's a polynomial degree 1. Not a very interesting one, but it's definitely a polynomial. So anyway, so this is Stirling's approximation. And generally when you do computer science, you kind of ignore the square root of 2 pi n part, and you just talk about the n to the n over e to the n part. And actually, technically, most of the time you can even ignore, this part and you can ignore the e to the n part, because the dominant term in this case is going to be n to the n. So notice that n to the n is not exponential, right? N to the n is what we call super exponential, because it's, remember when you defined what an exponential function was back in like algebra, that an exponential function has to have a base, right? And that base needs to be a constant. So here the base is a variable. So n to the n is a variable to a variable power. And that's just going to be huge, right? So anyway. Well, so here, there's a reason for that, right? There's actually a reason for us ignoring, and you know, so if you ever took physics, you'll understand what I mean, because you know you'll see some stuff that the physicists do, like, I think they'll do something, you know, you'll see approximations like, oh, sine of x, that's just equal to x, or natural log of 1 minus x is just equal to x, right? They just, I mean, everything's just equal to x in the physics approximations. But the point is that Stirling's approximation is a really cool thing. It's really useful for changing something that's like an n factorial into something that we can actually deal with, because remember, n factorial is only defined on integers, unless, of course, you're going to talk about the gamma function, in which case you should be in complex analysis, right? So the point here is that Stirling's approximation is just a cool little way of dealing with n factorials without having, you know, if you have an n factorial versus some other function. And I guess the last thing I'll say before we move on and get away from all this math is that you might be asking yourself, well, what about the other functions that I know? Like, what about sine of x, cosine of x, tangent of x, etc.? Like, what about those? You know, you don't care about trig. And the answer is no, not really. And the reason why we don't care about trig is because it's excessively rare. It's extraordinarily odd to find any function whose runtime, right, is O of sine of x, okay? It's very weird, okay? That would be a strange bit of world that happened, right? You know, it'd be like, okay, so you know, if the input size is like pi over 2, or if the input size, if we're using degrees, is like 360, then the sine of 0 is equal to the sine of 360 is equal to 0. And it's like, well, okay. I mean, you could kind of I guess you could design an algorithm that had the runtime of like sine of x, and not even really that, because unfortunately sine is negative for a lot of values. So my point here is that trig is generally ignored in computer science, and the reason why is there's no real algorithms that perform in like O of sine of n time or O of cosine of n time. It would be a bizarre function that did something like that. Okay, so yeah, it'd be something that I would not. I don't really know how to describe it, so I won't. So let's look at. So let's get away from math for the last part of the class, and get back to, hey, come back here. I didn't say you could go anywhere, PyCharm. Let's talk about BigO functions. Okay? So we've talked about searches. We've talked about sorts. Let's talk about some random functions, right? So these are not searches. They're not really sorts. But let's just talk about functions as and how you would actually look at their BigO complexity. Okay? So here's how you do it. Basically, let's make a function. And it really doesn't matter what the so generally, right, the list size is going to be what we call n, right? So the list size is going to be what we call n, and so basically whenever we ask what is the time complexity of this function, and it has an input size, which is like a list or a dictionary or something like that, then that list size is going to be what we call n. So, okay, let's say we want to count up all the, we want to just add up everything in this list. So for x in a list, right, we're going to have total equals 0, right, and then we'll do total plus equals x, return total. Okay, there we are. So here's the thing, right? So what's the time complexity of this function? And the answer is, well, how many steps does it take to run? And so let's discuss the number of steps, right? The number of steps it takes to run. And so the first thing that you see is that we're defining total equals 0, right? So you might say, well, how do I know exactly how many steps that is? I'm going to call that one step, okay? Now you might say, well, actually what it is it's 2 steps or whatever. Like maybe it requires, I think actually in this case it only requires one assembly language instruction to do, so it's basically 1 step. Let's see. Hopefully it'll get less blurry. But anyway, so okay, so then what else do we have to do? So what's the next step? So then you have a list here. So it says for x in a list, you add this. So let's call this 1 step, right? And then how many times does that step execute? That step executes however many times there are things in the list. So we're going to end up with is n times 1, right? And then we have a return statement, which is 1. So the total number of steps that it's going to take is n plus 2, right? And so the point is that what we're going to be able to say is that, so that's generally the trick. So the point is, the moral of the story, I guess, in the end, is that if you have n plus 2 steps, that is an O of n algorithm, okay? And you might say, well, why didn't we include the plus 2? The answer is because it's a lower order term, and you could say it's an O of n plus 2 algorithm. But the reason why we call it an O of n algorithm is because you should think as n goes to infinity, or really maybe not goes to infinity, as n gets large, right? Maybe n is equal to 1 million, right? Or 10 million. The difference between, say, 1 million, so 10 to the 6th, and 10 to the 6th plus 2 is almost negligible, right? So it's almost negligible. There's no real reason to track it, and so that's the reason why we just call it an O of n algorithm. Okay. So let's look at another thing. So this is an O of n algorithm. All right. So let's code, say, an isPrime function. So we'll have n as the thing, and then we're going to do a little bit of a trick. The trick we're going to do is that we will say for I in range, and then I'm going to say 2 up to the int of the n to the 1/2 power, so that's the square root of n, and then I'll just add 1 for safety's sake. So this is basically, how many times is this going to run? The answer is actually going to be, it's going to run something on the order of the square root of n plus 1 minus 2 times, or minus 1 time, or something like that. So basically what we're going to do is we're going to say if n mod I is equal to 0, and so think about what n mod I means. So if n mod I is equal to 0, that means that I divides n evenly, so that means that n is not prime, we're going to return false. And then finally, if we run through this whole thing and it doesn't do that, we're going to return true. Okay? So you might ask yourself, what is the time complexity of this function? And the answer is, well, how many times does the for loop run? The for loop runs something on the order of square of n times, right? So that's the point, right? It runs approximately square root of n times, and so this function is O of the square root of n. Okay, and that's it. That's really it. So, and you can write a different kind of is prime function. So you can actually write a less efficient. You could write a worse function, where instead of going up to the square root of n, you just go up to n. And these will both work. They will both produce false if the thing is composite, and true if the thing is prime. But this one runs in O of n time, right? And so if we look at our little graph, right? We look at our little graph, and we say, okay, here's O of n time, and then here's O of square root of n time. And then let's get rid of the natural log of whatever. So you notice that here, the square root performs really good compared to n, right? Here's n, and here's the square root of n, right? That's a good question. Why am I starting at 2? So, why start at 2? The answer is because n mod 0 is a division by 0 error, right? So you cannot mod by 0. Can't do it. And so I don't want to start, and I don't want to just do range n, so I can't do n mod 0, but then I also don't want to do n mod 1, and the reason is not that it's an error. The problem is that n mod 1 is always equal to 0, because think about it. When I divide a number, say 10, divided by 1, I always get that number back, so I'm going to get 10, right? So if I say n divided by anything, or I'm sorry, if n divided by 1 is equal to n with a remainder of 0, right? And remember that mod is always remainder. So the point is that n mod 1 is going to just always be 0. So it's never, so the point is it's not actually telling us anything about if the number n is prime, right? Because 5 divided by 1 is 5, remainder 0. But also 10 divided by 1 is 10, remainder 0, right? So it doesn't matter. So, okay. All right, so that's one thing to do. So basically what you're doing is you're just counting the number of times the things run, right? So that's kind of what you're doing, all right? So now let's do an example which is a little bit more complicated. So let's call this pointless counting, right? And let's go up to n. And so then let's say for I in range n, for j in range n, right? What we're going to do is let's make a total. Total equals 0. Total plus equals, let's say, I times j minus I squared minus j squared. Okay? And then we return the total. Okay? And so I'm going to ask, what is the time complexity of this function? And the answer is, well, let's talk about it. So what are the steps here, right? And you might ask, like, what is this actually totaling? And the answer is, who cares, right? we're not talking about what the function is doing. We're talking about how many steps the function takes before it finishes, right? It might dictate that it's n squared. Hint, hint. Yeah, it does. But I want to be more careful than that, right? So, okay, let me show you what I mean by being a little careful, but let's count the number of steps here. So the number of steps is 1 because you set the total equal to 0, and then we have this outer for loop, right, which is going to be n times the stuff inside, right? And so the stuff inside is equal to an inner for loop, which takes n time, times the stuff inside of that, right? And so what is the innermost stuff is equal to t is some assignment, right? And so basically what we're going to assume is that something like this takes constant time. And the reason why it takes constant time is because if you think about it, does this calculation depend on n? And the answer is once you pick an I and you pick a j, it doesn't depend on n, right? It just depends on I and j, and it basically is just adding, right? So we assume that all additions are going to take the same time. So we assume all additions take the same amount of time, right? And even though you might say, well, this is a bunch of multiplications and then additions and all kinds of stuff, it's all constant time relative to n, right? So our question is not, is it constant relative to I? Is it constant relative to j? Is it some, the only variable we have is n. And so that's the question, right? We assume that assignments, we assume if statements too, right, are constant time. And so basically we're going to say, okay, the innermost stuff is O of 1. And then what I'm going to do is basically say, okay, the outer stuff is n times the inner stuff is n times the inner stuff, and so we're going to end up with n times O of 1, which is equal to, as it turns out, O of n squared, right? And of course you might say, well, we have two extra statements. We have the total equals 0 and the return, but I don't care. I mean, it's the second one, I think, right? Yeah, remember that plus and minus, remember order of operations here, right? So the multiplication and the exponentiation will evaluate first. Well, first, I guess you would say exponentiation, right? This exponentiation, so they'll evaluate, and then the multiplication will evaluate, and then all the addition subtractions will evaluate. I mean, again, the point is, if you're looking at this calculation, beyond just saying it's constant time, then you're thinking too hard, right? Okay, so the point here is that this is an O of n squared algorithm. All right, let's do another example. So def matrix multiplication. So two matrices. So here's the algorithm for matrix. Let's make it matrix A, and let's make this matrix B. And so remember that both of these have to be 2 by, no, not 2 by 2. They have to be n by m matrix, which just means a list, right? This is a 2D list of numbers, right? That's all you really need to know. It's a 2D list of numbers. And then here, this has to be an m by, say, let's say this is n by k, and then this will be k by m matrix, which is another 2D list of numbers. Okay? And so what we're going to do is we're going to return A times B as matrices. So let's do that, right? So let's see, for I in range len matrix A, for j in range len matrix B, 0, and then what we're going to do is we're going to say result matrix ij is going to be equal to 0. Well, okay, let's say result matrix is equal to an empty list. So then what we'll do here is we'll do result matrix dot append an empty list, and then here we'll do dot append 0. That way we'll have I and j, and then what we need to do here is for let's see, k in range len matrix a 0, and then what we'll say is result matrix ij plus equals what is it? Matrix A ik times matrix B kj. And of course, here's the thing. And I saw some people mention linear algebra, and so I'm doing this problem. Now you might say to yourself, I don't know linear algebra. I haven't taken 221 yet. I have no idea what's going on here, right? But the point is, you don't have to know. You don't have to care about linear algebra, right? We are going to compute the time complexity of this function without understanding, right? And that's the great thing. We don't have to understand matrix multiplication to compute the time complexity of this function, okay? So, all right, so let's compute the time complexity of this function. So we notice that we have 3 loops, right? We have this outer loop here, and the range len matrix A. So I'm going to assume that this matrix is of size n. So the outer dimension is of size n. So basically here we're going to have n times the inner second loop, right? So second loop is going to be, well, so here, technically, this is k, right? So it's a different size. So we have 3 different sizes here. And then what we're going to do is we're going to say third loop is equal to, actually, no, I'm sorry. The second loop is equal to m times third loop. And third loop is going to be equal to k times inner calculation, right? And inner calculation is going to be equal to O of 1, right? Because you might be saying to yourself, I have no idea what this thing is, right? This is a bizarre, you know, intractable calculation, but who cares, right? It's O of 1. It's literally a plus equals, right? And a multiplication. So that's O of 1, right? You don't have to understand what it's doing to be able to compute its time complexity. So it's O of 1, and so then here the total time is going to be equal to n times m times k times O of 1, which is just equal to O of nmk, and that is equal to the time complexity for matrix multiplication, O of nmk. Now, generally, if we assume, so there's a simplification that we're going to make. Assume that n is equal to m is equal to k. So if we do that, then what we see is that if we have O of n and n, that's equal to O of n cubed, right? And so you see here, like, that's kind of the idea here. You don't need to understand matrix multiplication to be able to compute the time complexity of this function, right? And all you have to do here is basically say, I see that this is some kind of algebra, some kind of arithmetic, it's O of 1, right? Computers do arithmetic in constant time. That's the assumption we're making. And then here, this loop is going to run k times, this loop is going to run m times, and this loop is going to run n times. So it's nmk. The answer is that, well, so there's not really a max or a min. Like, this is, basically what this is doing is this is assuming that we have, here, this is assuming that we have 2 square matrices, right? We have an n times n list and another n times n list. And if we make that assumption, then this whole thing runs in O of n cubed time. So that's the point. But I think it's important to understand that there's a lot of functions that you're not going to necessarily understand exactly how they do their calculations, but you can still compute their time complexities. So here's an example of an O of n cubed. This is a non-trivial O of n cubed algorithm. This is an algorithm that actually, I mean, I shouldn't say that, but it needs to be O of n cubed, right? Because O of n squared is not going to work. There's actually, unfortunately, there's some slightly better time complexities out there for matrix multiplication, but the algorithms that are required to do those multiplications are extraordinarily more complex than this, and so that's why we're not talking about them. So I think the current thing is like about O of n to the 2.3 or something is approximately, is approximately the best for matrix multiplication. But again, who cares? So let's do another one. So here's loggy time. So I'm going to tell you that this is going to be log time. And let's think about why this thing is going to be log time in just a second. So I'm going to say while n is bigger than or equal to 1. And so then what we're going to do is n divided equals 2. And that's it, right? Maybe what we'll do is we'll say count equals 0, count plus equals 1, and then we'll return count, right? We don't have to actually do any of that. All of that just adds O of 1 extra time, but whatever. So the question is, why is this log time, right? I'm going to tell you, right, that this is O of LG of n time, right? And so your question should be, why, right? And the answer is, think about it this way. So what if we have, let's say that we have something like, let's say that n is equal to 16, right? If n is equal to 16, then 16 divided by 2, I don't know, let's even just do integer division. So 16 divided by 2 is 8, right? 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1, 1 divided by 2 is 0. Okay, so the count that we would get in that case is, I guess, 1, 2, 3, 4, 5, right? We get 5. Which, as it turns out, is 1 plus the log or whatever, but who cares? So, all right, but what about if we do something like 32? 32 goes to 16, which goes to 8, which goes to 4, which goes to 2. So instead of getting 5, we'll get answer is equal to 6. And then here, if we do, say, 64, we'll get the same thing, except now it's going to be one more step, so answer is equal to 7. And so the next one is 128, and we do the same thing, right? So now you might be saying to yourself, well, okay, you've proved to me that this is increasing the number of steps by 1 for every time we increase the n by a power of 2, right? But the numbers that I've given you here are pure powers of 2, right? 16, 32, 64, 128, all these are just pure powers of 2. So the question is, what about non-pure powers? And I don't know that that's an actual term, but what I mean by that is something that's not exactly like 2 to the k is equal to n, right, as some integer, right? So basically, for instance, like there are a lot of numbers for which there's no k, such that 2 to the k is equal to n. So 17, for instance, right, is equal to 2 to the k. There's no k, so that, I should say there's no integer k, so that this works, right? But what if we do something like that? So let's look at, say, for instance, 345, right? And we divide this by 2. What do we get? So we get something like, let's pull up the Windows calculator for no reason. So 345 divided by 2, that's equal to, it's 172.5, but let's do integer division, so 172. And then here we'll divide this by 2 again. And so then we're going to get 86. And then what do we get next? We're going to get 43, right? And you might be thinking to yourself, like, I don't understand it. How are these all powers of 2, blah, blah, blah? Like, they're not powers of 2, but again, 43 divided by 2, that's 21. Again, ignoring all, right, 21 divided by 2, which is 20 divided by 2, that'll be 10. And then we'll get 5, 2, 1, 0. So, in total, we're going to get is 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. Right? And so the question is that approximately log of 345? And the answer is, well, remember the base change formula. So we do 345, take the log of it, and then we divide it by 2, take the log of it, and hit enter. And so as it turns out, that's 8.4, right? 8.4. And you see that the answer that's going to pop out is 9 steps. So the answer is 8.4 is approximately, right, the log. And so the answer is actually, yes, it approximately is right. So that's pretty nice, right? So that's the idea here. So is that something like this, something as simple as this can run in something like logarithmic time. So it doesn't run in n time. It's not square root of n. The reason why it runs in log n time is because of this dividing by 2 thing, right? Because the definition, remember what the definition of log is. The definition of log is the number of times, well, I guess LG, right, is the number of times you have to divide by 2 until you get down to 1, right? And I mean, you can say, well, there's sometimes decimals, right, with, caveat decimals exist, but really the point is that who cares, right? So the definition of log is the number of times you have to divide by 2 until you get down to 1, and the reason why that's the case is because remember that the definition of log is that LG of x is equal to, say, y, when 2 to the y is equal to x, right? And so you say to yourself, I have to divide x by 2, y times, right? Well, I mean, so there's, there's basically 3 definitions of log. So the 3 definitions of log are, well, so actually, this is equivalent to the algebraic definition of log. The other definition, of course, is the integral from, say, 1 to x of 1 over x dx, right? So that's also natural log of x, right? So that's one definition. The other definition is that's the inverse of exponential. But of course, what does that mean? What that means is that if you have something where 2 to the y is equal to x, then the log of, or I should say LG of x is equal to y, right? And so again, that's just basically what this is saying is that 2 times 2 times 2 times 2 times 2 times 2 y times, right? And now you might say, well, you might have to do some kind of decimal thing where it's not exactly and blah, blah, blah. But we're being approximate here. So that's what it means to be the inverse of the exponential, right? So your definition is actually equivalent to this definition. So theoretically, you might have to multiply it like 4.7134 times by 2. And of course, that's the question is like, what the heck does that mean? And the answer is, who cares? But yeah, the point is that so this function runs in log time, and that's really all you need to know. All right, so we've gotten some good examples here. We've seen an O of n squared function. We've seen an O of n function. We've seen an O of square root of n function. We've seen another O of n function, and we saw a log n function. So we saw a bunch of different functions that run in different times. And so I think this is basically where I want to leave it with BigO. So basically the idea here is that what will we ask you to do on an exam? And the answer to that is it's going to be complicated. I have been leaving off BigO in general, but I might, if I put it on, it's going to be something like, what is the BigO of this function? And it will not be something like, log of n factorial times 2 to the n times whatever. It's going to be something like n squared, or n cubed, or n, or maybe square root of n, or something like that. It's going to be one of the things that are basically on this list. Okay? So, all right. That's all I've really got. I think next time we'll talk about some other stuff that's, Okay. I'll let everybody go now. Yeah. Have a good day, everyone.